Welcome. Programming Basics is the overarching theme throughout all of the sessions that we're going to be having in this week. All right, let's get into it. So I start with the acknowledgement of country that we here at Curtin University in Perth, that the Whadjuk Noongar people are the traditional custodians of the land on which Curtin University's campus lays here in Perth, and I pay respects to elders past, present and emerging. This week, just have a look at the unit learning outcomes. Not for a great length of time, no more than 3 to 4 hours. No, just joking. So, why are these important? Well, the unit learning outcomes is what drives all the content within this unit, and actually should be within all of your units. So everything we do ties back to these unit learning outcomes. So identify appropriate primitive data types required for the translation of pseudocode algorithms into Java. What? We're going to tackle some of that today. Design in pseudocode simple classes and implement them in Java in a Linux command line environment. All right, so our third unit learning outcome is design in pseudocode and implement in Java structured procedural algorithms in a Linux command line environment. So you can see already that this thing called pseudocode is coming up a lot, algorithms is coming up a lot, and command line environment is coming up a lot. We talked about command lines last week. Apply design and programming skills to implement known algorithms in real-world applications. So we're going to be taking, and really designing and programming up algorithms, things like file reading, data processing, these kinds of things, and applying them into semi-real or real-world applications where you could apply them. And the other thing we want to do is reflect on design choices and communicate design and design decisions in a manner appropriate to the audience. What do we mean by that? We need to be thinking through the decisions that we make when we're designing programs. Why are we doing things? And then we need to be able to communicate these. And we need to be able to communicate these well because our clients, our customers are going to need to know why are we going to do it that way. Now, if you're one of our postgraduate students, our unit learning outcomes are slightly different, but develop and apply simple, non-object orientated algorithms. Okay? Develop and implement simple classes in an object-oriented language. That's what we're going to be doing with Java. Create object-oriented designs consisting of classes connected by aggregation. And again, similar to the undergrads, communicate our design decisions in a manner that's appropriate to the audience. These are absolutely crucial things for this unit. So our outline for the set of talks I'm going to be giving is this. Development Java, we're going to write some Java, we're going to look at variables, primitive type strings, and then we're going to wrap up with user input. So let's dive in to development. So development. What is it? Well, software development, there's a set of stages or a set of 4 or 5 things we need to do when it comes to software development. You need to understand the problem. If you don't understand the problem, you can't solve it. It doesn't matter how good a coder you are. If you don't listen to your partner, tell you what's wrong, you're not going to solve your problems, okay? You need to listen. You need to understand what's the problem. It's a bit small, but never mind. We've got to define the problem. Define it clearly. Articulate what is the problem we are trying to solve. Because really, software development is that. It is problem solving. Oh, no, it's not. Yeah, think of your apps on your phone or your tablet or anything you use where you've got an app. The app really is just a problem solver. That's all it does. Oh, but it's Candy Crush. Well, it solves the problem of boredom, okay? But think it through. It's actually solving a problem. And to solve a problem, we need to be able to define it. To do this, we need to be able to think, consult, revise, do all kinds of stuff like this with people to understand what the problem is. Then, once we've understood it, then and only then can we design a solution. You can't design a solution if you haven't understood the problem. We design a solution, we specify what are the steps involved in doing this, okay? We create algorithms. So we find the steps and then we create the algorithms that we're going to go through to get stuff done. Next, we test the solution. The solution that you've created, that design, does it actually work? Okay? Does it work in theory? We haven't done any coding yet. Okay? Then, after we've tested it, we fix it because the chances are you found some flaws in your design. So we're going to fix those flaws. Okay? And now, our final stage is write the code. And not just write the code, you will notice it, excuse me, it says write and document the code. And that's really important that we document the code. And we need to, when we're writing and documenting, we test the code. Does it work? And ensure the code is maintainable. And we do this through things that we're going to see later on, like comments that we'll write. It's well structured. All right, it's important that it's well structured. Okay, it's logical. It flows. And it makes sense. These kinds of things are what help make our code maintainable. Maintainable so that others who come after us can actually know what's going on and then fix, add, modify to it. So defining the problem. We need to understand what's the problem that our client, our customer needs solved. If we don't understand it, there's all kinds of things, but basically you're up the creek without a paddle, okay? And one of the keys when you're understanding the problem is understanding the problem, and then what you want to do is you want to articulate it back to the client. And the reason you want to do that is you may think you've understood the problem, but have you? By articulating it back to the client, they'll be able to go, yeah, that's it. Or no. And that actually doesn't mean you got it wrong. It may mean that their communication of the problem was wrong. And you can resolve those things up front. So we start with a top level general English description of the problem. Okay, that's it. Stating what data is required to solve the problem. What are we going to need? Well, if we're going to create a program that calculates the average temperature in the months of this year, we're going to need some temperature data. We're going to need to know what day that temperature we're on. That kind of information. What's the input data coming into our program? What are the results that are going to be calculated? Well, I said that one. So we're going to be calculating, one of the things I said was the average temperature. So that's going to be one of the outputs, one of the calculators, the output data. That's what it is. What else do we have? Well, what action do we need to do? If I've got this kind of information, okay, I'm going to need to do some things to work out what is the average of those things, okay? So that's the action item, or the actions that are going to take place. There's going to be some sums, there's going to be some division. That's to start with. Simple example, but really, really important. Okay, designing a solution, the algorithm. So what is an algorithm? That's just the one letter. So algorithm, we say, is a set of detailed, unambiguous, ordered steps specifying a solution to a problem. Okay, let me rephrase that. You can't put the cake in the oven to bake if you haven't mixed all the ingredients together. Okay, so we need to know detailed, unambiguous. What order do we do them in? These kinds of things. Using my weather example, we need to get the weather for each day, the temperature. We need that, okay? Need that, and then we need to do some calculations. What steps need to occur? In our one, we would say something along each day's temp is stored. Okay. Once all days temps stored, add them together. Okay, that's not the full steps, but that's now articulating. We're getting each day's temperature is stored. Once we've got all the day's temperatures, then we add them together. Next would be to divide. I think you know how to calculate the average. So our description is independent of programming language. You'll notice in that description that I've written, there's nothing of code, nothing like that whatsoever. And I could even say, divide the sum of the temps by the, whoops, and I've got things piling up. Anyway, I've lost my writing. Never mind. And now I'm flicking through everywhere. So let me just go back a little bit. Here we are. Okay, so English description of the language, of the problem, English description of the language. Non-trivial problem is going to require lots and lots of non-trivial things and refining it to ensure we've got it correct. And there's a bunch of different ways we can go about doing them, okay, and designing this kind of solution, this kind of algorithm. We're going to be talking a lot in this unit about pseudocode. Okay, now pseudocode. I always say to people, if you think of pseudo echo, and if you're going pseudo echo, great band of the 80s, go home and ask your mum and dad about it if they're from Perth. Okay, tell them they still play. But pseudo echo, not a real band really. They were like, anyway. So pseudocode is not code. It's pseudo, not real. Fake, okay? And what it is, they're these English-like phrases that describe the algorithm steps. And you saw that when I was writing those things out. That was the start of my pseudocode, okay? Simple, straightforward. I've said it already. I'll say it again. It is not a programming language, okay? It is pseudo. Please keep that in mind. Developing pseudocode is about refining the steps within your algorithm so that when it comes to coding it, you can get it done reasonably quickly and reasonably accurately the first time around. It's not always going to work the first time around, but we want to refine it to make sure, have we got all the steps? Have we missed any steps? Have we missed any data? So, I say developing an algorithm is a journey, and that's what it is, because it's on the journey you realize what you've missed or what things you don't need. Okay, if you think of traveling, I have a travel list. Now, my travel list that I run through every time I go on a trip didn't appear out of nowhere. Almost everything on that list is there because at some point in time I forgot it. Okay, and then if I take everything on all of them, sometimes I end up with too much. So I have had to refine those lists into long haul flight lists, short haul flight lists. How long am I going for? These kinds of things. We develop the algorithm step by step, and on that journey, what are we missing? Now, people want to tell you that computer programming is science, and there is a science and there's engineering to it, but there's a huge amount of design of art, okay? How are we going to get there? How are we going to do it? So algorithm design is an art. It's an art form, and it takes practice, okay? 20 years down the track, I am still practicing my algorithm design using pseudocode. When we're writing pseudocode, what's really important is that it is clear, okay? Absolutely clear. What does this mean? It needs to be logical, okay? Because the computer works logically. And when it gets into the computer, it needs to be logical. So it has to be logical. It needs to be understandable. Now, it needs to be understandable to you and to me as humans. And the reason for that is important because you, me, your team will be the ones who are writing up the code from the pseudocode. So it needs to be understandable. It needs to be consistent. You need to do it in a consistent manner so that when people see it, they know what's going on. What's been, well, this is different from the last time I saw. What are they doing here this time around? We don't want that. It needs to be consistent. And lastly, it needs to be correct. Okay? So I call this, people have a bit of fun when they hear me call it this, but it's really the cluck message. Okay? Clear, logical, understandable, consistent, and correct. Which is the most important of them? Well, the most important is all of the ones that have a tick next to it. So let's have a look at some really simple pseudocode. Okay, what are we going to do? Well, we've got to write a program to sum two numbers that come in from the keyboard. All right, that's pretty good. And we're going to output the result to the screen. Okay, we can do that. Here's our algorithm. Okay, I say main to start it, and now I say input. So I'm getting input, and I've called it, really complicated, num1. So the first bit number I get in, I'm going to call it num1. Input num2. So I've got the first number, now I've got the second number, and then I say sum equals num1 plus num2. Pretty complicated stuff. And now I output sum. That's it. End main. I've ended my algorithm. So that was pretty straightforward. And that's what pseudocode is all about at the end of the day. Like I said, it's not rocket science, it's not fancy, it's simple, straightforward English description of what needs to occur. Now we test the solution, and I say we desk check the algorithm, walking through it step by step. Was it complete? Did it do what it needed to do? And if we think about that one, I got num1, so if I say input num1, remembering back to it, I'll say my number was 3. Then, okay, was it complete? Did you get all the way through the logic? Next step was input num2, I'll say I'll put 4 in, and then the next one was sum equals num1 plus num2, 3 plus 4. All right, I think that's right. Now, provided in our situation, sum was going to be that, which we would say 7, and then we said output 7 and go, I reckon we got that right. We desk checked it and we got the correct answer. So our algorithm, step by step, is good. Now, if we answered no to any of the above things, we've got a problem, and we go back and fix it. That's all. Fixing the solution. This can be in many places, but generally we return to understand the problem, okay? Return to understanding the problem and see, where did I not understand the problem, okay? What did I misunderstand, or what did I not understand? Design the solution. You can see we're revisiting our steps. We fix our design with our new understanding of the problem. We test our new design, okay? And our testing of our new design was from understanding the problem better. We walk through our test cases. So in that 3 plus 4 and see, did it work? Okay? Did you answer no to any of those questions? All right? And when we go, oh, we're back, we recycle and go again. Rinse and repeat until the solution is correct. Writing and documenting the code. We've got our code, and now we need to implement that, I say, in a high-level language, and we're going to implement it in Java. Now, something that's important is, Java is not, or pseudocode does not map one-to-one. So one line of pseudocode does not necessarily mean one line of Java. So if you write your steps out and you find your actual Java code is much longer, that's okay. All right, so we're converting it. I said that is code the solution. So we've got our solution and we're now coding it up into, in our case, Java. All right. So to do that, we need to know the semantics and the syntax of the programming language that we're going to be using. And in our case, it's going to be Java. And that's part of this unit, is learning Java. Okay. The files that we create are called, of the high-level languages, are our source files, I should say. So if we write Java, which we're going to, then what we're going to get is our Java files are our source code files, all right? So that's really important to keep that in mind. And now we write the documentation so the code can easily be maintained. That's straightforward. That's some basics of development.